Hello, welcome to our next lesson, and we will be discussing today problem of image segmentation. So we'll start with the statement of the problem, and I'll introduce you to the early models, and we'll think about some naive ideas how we can use convolutional neural networks to tackle this problem. And at the end of this lesson, we will get familiar with state-of-the-art models for this problem. So what basically is image segmentation task? So when we have some image which is represented as an array of numbers, we probably want computer to understand what's on this image. So the first problem is classification. Basically, the ImageNet competition is for the classification problem. But what if we want to find where the object is? So, for example, if we have a surveillance camera and we want a computer to recognize where the person is walking and where are all the cars. So this is much more complicated problem because, for example, for classification, you just need to predict only one number, the label of the class. And for detection problem, when you are trying to find out where the object is, you are trying to predict one number of a class and four numbers for a box around this object. And the situation becomes even more complex when you have several objects, so you want to detect every object. And we will be discussing now the most complicated version of this problem, image segmentation. So this problem is to detect class for every pixel on your image. So it is basically the conversion from image from an array of numbers to another array of numbers, so like another image, where every pixel denotes some class. You can see on this cityscape image that every person and every every traffic light is somehow colored. This is overlapping the second image that the neural network will predict on the input image. So let's just think about how can we use such an algorithm that can predict a pixel class for every pixel of our image. For example, we can use this for self-driving cars when we want a camera from a car to detect where are the other vehicles and where are pedestrians. We want probably to use this for traffic control systems, so some camera will record the traffic conditions. And for video surveillance, also these algorithms are highly used in medical diagnostics and medical pathology mapping. So when you have an image of some human organ, for example from an MRI scan, you want to determine whether this patient has some disease or has some pathology or not, and it's quite often really hard to determine where are boundaries of different organs. So you can here see the X-ray image of the lungs of a human and the segmented image where all the organs are mapped. And here is a scan of retina, and these all are cells. So basically here the task is to determine different cells. But we will discuss the semantic segmentation, where the two different objects are considered the same class. So we will not make a difference between different objects. More on this later. So let's just recap how any image recognition or image classification problems are solved. So on the ImageNet competition, there was a huge success in 2012 when AlexNet network outperformed all other models. And after that, basically the era of convolutional network began. You probably know that convolution, it's like a tiny filter that applies to every patch of this image, and you can stack all these filters one after one, so you can get, instead of 3 channels, red, green and blue, you can get plenty of them, and you can just obtain somehow another image that is in somehow transformed way. So you are probably familiar with convolutions, and you can see that all these models are just becoming more complex and more deep. And in 2016, there was a really interesting idea from Facebook just to connect the output from the previous layer to the next layer. So basically, it's like copying values from here and pasting them here. So this part of network just can perceive what the values were here. And this idea of residual connections is highly used in problem of image segmentation. Here you can see the graph of various performance of different modules. This is AlexNet, which was the first, and here is different ResNet models. Okay, so let's just dive into our task. So we have here a picture, and what we want is some kind of map where on every pixel there is a number that determines what class this pixel belongs to. So for example, we have here like something like a tree, and we want our network to label all the pixels in this region as to some number which corresponds to a class like plants and grass, and basically we are creating a heat map for every object, for every class. So here you can see how what will be if we overlap the predictions and the image that we were mapping. The same picture was with that cityscape image. This map of several pictures can be represented as several maps where we can have only 2 values. We can have only zeros and ones. And we have several of these maps which, for example, if we have n classes, we will have n these maps. And every map is determining something like probability of the model that the value, the class of this pixel, of the particular pixel, is belongs to every class. For example, if we have for a classification like this pixel, the neural network will output an array of numbers that will correspond to probability that there is a person, and so that there is grass, or so there is, for example, a pavement or building. So basically, these kind of neural networks, they're trying to predict, they're trying to solve the classification problem for every single pixel, but they need to use the information about near neighborhood of this pixel. So it's kind of a lot of neural networks that run the classification problem that you're familiar with, but they run it for every single pixel. and if they output one hot encoded vector, you can just think of them like as of several maps that are then overlap one of top of each other. So how people solved this problem before deploying? They solved a slightly different problem. So they were trying to find some regions on an image that are similar. And they were trying to then interpret these results. For example, if you have something like a kitten, a red kitten on the green grass, the idea is that the pixels that belong to the same class are somehow more similar than pixels that belong to different classes. So basically, using this idea of distance between pixels, which can be determined as sum of squared differences, a square of differences. Using this idea of distances between pixels, you can run basic clusterization algorithms like k-means, and you are treating every pixel as a point inside a three-dimensional space. There are plenty of other methods, like histogram-based methods, when you just you plot some histogram. Let me draw it. So you have like histogram. Yeah, here there will be occurrences, the count of pixels that belong to a particular, for example, luminosity. We have luminosity here, or it can be an red channel amplitude, or G or B. So you can plot these histograms for several values, and you just plot something like that. And basically, if you obtain this situation when you have different bunch of pixels near some region, you can assign this one to class 1 and this one to class B. And this is how the early segmentation algorithms worked. There are some other algorithms that are more complex. For example, when you're trying to take into account what's the length of this region. So this picture is a clusterized picture where every one color region was obtained by k-means clusterization. So this is considered the one class, and for example, this is considered one class. Yeah, these methods are not very useful because you can't determine different classes that are like the same color. If you try to find, for example, green ball on a green grass, you will never obtain good results. Yeah, so we need to use the context of that pixel and to utilize the context of that pixel, you apply something like, so you have an image, a grid of numbers, and for example, we want to predict a class for this image. We have 3 values for this pixel, yeah, R, G, and B. These are 3 numbers from 1 to 256. And if we try to use only this information, we cannot determine like the green ball on the green grass. But if we try to use something, some model that takes a neighborhood of this pixel, takes every pixel here, yeah, all these values. For example, it will be, I don't know, 5 by 5 square, and you put all this square to some model, and model outputs us a label of this class, 1, or I don't know, dog. It can be anything. Okay, so when you try to use the neighborhood, it is very important to decide how you use these values. And the early methods were using some so-called filter banks. So when you apply a filter, these images here, they're just representation of filters, and these filters are arrays of numbers from 0 to 1. Yeah, it's like a black and white image. And so what they were doing, they were taking this filter and multiplying every pixel here by value that corresponds on this filter, and just summing it up. And they obtained some values, I don't know, 0.57. Yeah. Don't draw near the edges. So we obtain some number by multiplicating by masking these images and then adding them up in some number. And if you have several of these filters, you obtain several numbers for each filter. So basically the output from one patch, from one neighborhood of this pixel, will be an array of numbers that correspond to every filter, from 37, yeah, 0, 1. And this array of numbers, it's like the result of convolution network. Okay, so then on these vectors, people were performing some clusterization methods, algorithms, the same way they were using, they were doing it on the pixel, in the pixel space. Yeah, so, and I didn't say that you first apply a filter here, then you just apply a filter around another pixel, yeah? So you obtain like the new image, but with not the RGB channels, but with channels that correspond to every filter. Okay, so let's move forward to deep neural networks algorithms, which are significantly more performant in comparing to the previous filters, because those filters are like hand engineered by the scientists, and here we will try to think about how we can solve the task with, for example, AlexNet from 2012. So the first naive idea will be, I don't know, maybe you have some other idea, but if I was thinking about this task with no prior knowledge, I was thinking about just let's take the whole network, this whole network, and apply it to a small patch of image, and just predict the label for every patch of this image. Yeah, so we look here, we'll find a cow, we look in another place, we find a grass, yeah, and for every small patch we obtain results of classification from this model. But there is a big disadvantage of this approach, we need to run this neural network for a lot of times, and it's and you do not use the information when the windows are overlapping. So if you think about it, when you're applying, for example, a patch here, it can be arbitrary size, it's up to you, and it depends on the network model. So when you evaluate network for two different squares, these pixels that here overlap, you are computing the same thing twice. So if you recall how neural network works, it uses even smaller patches here, and applies some filters to it. And when you apply a filter here, you're computing the same thing 2 times. So this is a terrible idea. It's computationally really ineffective. But what if we try to use not a classificator, but some model that will already output our scores without predicting the class. So we just put an image, into a convolutional layer and stack some of them, and have our scores for every pixel. So basically, this means that when you are applying a convolutional filter, you just do almost the same as in here, But here you apply the whole network, and this network contains the filters that are sliding across this patch. But instead, which is better is when you apply the whole convolutional filter, the whole convolutional layer to an image, and these convolutional small filters, they are applied to a small region and output the predictions. There will be a number of some linear models that are applied to the small patch of image, and they, if you have, for example, 10 classes, you will need to have no less than 10 filters, 10 different filters that are applied to every square patch. But this method is computationally expensive if you stack several convolutional layers one on top of each other, which is what gives us the advantage of deep learning. And if you don't downscale the image, this model will be really computationally expensive. So the solution is to use downsampling layers, something like max pool. You're probably familiar, but if not, the idea of max pooling is following. For example, you have a max pooling layer with a parameter, let's call it a receptive field, 2 by 2 pixels, and for what it does, it applies the following transformation to every 2 by 2 pixel. It just takes the maximum value and outputs only the maximum value. So on the input of max pool filter, you have 4 pixels. On the output, you have 1 pixel, which is maximum value. And you apply this filter to every 4 pixels that are adjacent to each other, just like almost the same like as in convolutions. But when you apply the max pooling layer, for example, with this configuration, you obtain a 4 times smaller image. It's 2 times smaller width and 2 times smaller height. So you can try to downsample this image, but there is a difference from, for example, object classification models, because when you're trying to classify an object, you don't care about information, about conditional information, about information of where this object is. So intuitively you need to store a lot more information about the image. So these layers have to be thick. They have to have a big number of filters to store all that information of relative positions of these objects. So if your convolutional network that solves classification problem, if you have like some part of your convolutional filters say that, yeah, I found a cow, and this information should just flow to the end, and you just need to say, yeah, there is a cow, but in this solution, you need like to store this information. Yeah, for example, there is a cow in top left corner. You need to store this information here. Yeah, and do not lose it. That there is a cow in that particular region. And then after you have something like encoded, and the good thing about this architecture that these inner blocks, they're analyzing information from a wide receptive field. So these filters are looking at this window, and the values from this window were obtained from a wider part of an image. Yeah. So a filter here, he is basically using the high-level information, not just a small, like you're not looking at the small patch of image, you're looking at a big, somehow pre-processed big image. And after that, you need to upsample this encoded information into this beautiful map. And the big question is, how do you upsample? So when you have this, for example, it will be like on this picture, height divided by 4 and width divided by 4, you need to somehow convert this this output of some filter of some filters. You'll need to transform it to 2 times bigger picture, and then apply some additional transformation to that. So let's just discuss how we can upsample this. How we can upsample our filter images. So let's just recall about what convolution is. It's when you apply a tiny model that takes only a small square patch of image. You apply this tiny model. It's like looking on an image inside like a small tube, yeah, and you're looking only at a particular region at every point, and just put in a table what you have found in that region. Yeah, so you have a table of observing results, and these squares represent the receptive field of these small filters. The outputs are put in another table in another filtered image. So yeah, but how do you reverse this operation? You can imagine padding the obtained filters, the obtained results from filters, padding them with 0 values, and then applying the same convolution again. So in this, when computing this value, we will look at almost every 0. We will see almost everywhere a 0, and only one non-zero value will be in this receptive field. So we will be just multiplying some one coefficient by this value and putting it here. And the same stands for these corner regions. When we apply, we have these receptive fields. But for this for this pixels, we will have two pixels that are non-zero, and so on. So this is called transpose convolution, or sometimes it's called up convolution. Yeah, so here is an example, a really nice mathematical example with lots of values, but it's quite easy. So this is one-dimensional example when you have not a two-dimensional grid, not an image, but rather a line where you have several values, like just an ordinary array. And the convolution basically is when you look at a particular part of this array and output some number. And you can represent this as this fancy matrix. It's just composed of these rows of the size of our receptive field. So when you multiply this one by this vector, you're looking at the first three values, and these are zeroed out. And when you're applying this row, you're looking at this one, and so on. So you obtain, in this case, four outputs for this filter. So this is only one filter. If you want to obtain the second filter, you just apply a second matrix, and the output will be one vector from one filter and the second vector from the second filter. And the point is that these values are the same. So the filter basically is not all this matrix. The filter is determined by this coefficient, that they are the same for every single row of this matrix, or for every. So this structure of this matrix just denotes that we are looking at several different subvectors of our initial vector. And as you know, the input and output dimensions of linear transformations, which are basically matrices, they correspond to the size of matrix. So if we want to take a vector of length 4 and obtain a vector of length 6, we can just transpose this matrix and apply the transposed version of this linear transformation to our lower dimensional vector. And you can see that it's really nice mathematically. It can be written really nice mathematically. So remember, yeah, when I was talking about that only one value will be non-zero, so this value will be, for example, this A and this B. So A will be just some number times B. There will be no summation over other coefficients. And here is the same, analogous situation when you basically like pad these small vectors with two another zeros, yeah, and this corresponds to a slightly wider matrix. I don't know if if my drawings are clear, but yeah. So if you apply convolution here it should be x. If you apply convolution that just filters on this vector, you will just obtain the same result as you just truncate this matrix because of here we have only 0 values. Yeah, but this is holds true only for stride equals 1. Recall the stride is a step. This step where of how of the amount of pixels that we are moving through our image. For example, here the stride will be 1, and if we had this situation x y x and x y x, and here will be 2 zeros, yeah. So there here the stride will be 2. And the transposed version of convolution, the transposed version of this linear transformation is analogous to convolution only when the stride equals to 1. Otherwise, it's a bit more complicated. So let's just recall. So we studied how we can upsample the image, and we apply upsampling here and apply upsampling in here, and just obtain some results. So on the end we have some filter that takes a patch of image and outputs a vector that corresponds to every class. So here the number will be corresponding to dog, and this number in this vector will correspond to, for example, cow. Yeah, and this is then fed into a loss function to minimize. And there is a really interesting proposal. So what if we not only upsample here, but when upsampling we just attach or concatenate output of encoding architecture. So when in this case, we are not using these outputs of these filters. They are used, but they are used not in direct way. They are used like as coefficients when we sum up here. But the proposal of the UNet network is to use these values and just put these values up on top of output of filters that are applied to this part. So the UNet is because of this really nice picture that is like in the form of letter U. So the idea is to take these convolutional features and you just stack them up with the output of obtained from whole this long transformation sequence. Yeah. So this model was used in medical purposes for determining something like lung cancer, and for yeah, I have a picture. They were trying to segment different cells. So this basically is slightly more complicated problem when you not only select objects of different classes, but you select when you're not only classifying the object, but you select different objects of same class. And here you can see the input name image to the UNet and the output image that produced different objects. Yeah, and the generated segmentation mask that only outputted whether there is a cell or not with the different classes, different objects, is here. So you can pay attention to how the network manages to determine borders between different objects. So again, the main idea of this architecture is to use information inside the encoded, and basically the most popular models nowadays, they use pre-trained models, pre-trained on ImageNet competition models like VGG19 or like ResNet. They use the pre-trained models and they train only this part, but they use outputs from these pre-trained models into into their like decoder architecture. Yeah. So let's just talk about how we train our models. So how the loss for our minimization problem will look like. Just recall that we are producing, given an n classes, we have n classes in the whole dataset, and the whole dataset is labeled. So the dataset that we are training on, we have an image, an input image, and we have basically it should be the same size. So for every pixel of input image, so let's say here is a kitten, yeah, and for every image we have a mask that says here is the kitten and here is, for example, background. And in the database we have something like a table, yeah, that corresponds. Here we have only ones, only values 1, and here we have only values 0, and here and in dataset we have a table that corresponds 1 equals to kitten and 0 equals to background. And we know the length of this table. We know how many classes are in the dataset. Yeah, and the neural network will predict a map that predicts the probability of each class in each pixel. So for this particular pixel, you output a vector that is of size n. Yeah, this is n, and here will be probability of first class, so let it be like kitten. Probability of kitten, here will be probability or confidence of network of second class, and you obtain this vector is for every pixel. So when you stack vectors like in this fashion, yeah, you obtain you get the image which is like this is the height is n, number of classes, and basically it's quite similar to convolutions, yes, and I'm describing in these details because you need to understand how this loss is compared to the ground truth. So how the ground truth will look like. It will be the same vector of the same size, but it will have only one, the all values will be 0, and only one value will be equal to unity. So, for example, we obtain our network outputs a vector like 0.2, 0.5, 0. Here, for example, here is our output, yeah, and here is the ground truth for this particular pixel. And what we do, we just compute cross-entropy loss for these two vectors, and then we just average this value, this cross-entropy loss, for all our pixels. So we just sum over these values. And if you're not so familiar with cross-entropy loss, basically it determines how similar these vectors can be in terms of probabilities. For example, if you have a coin, yeah, if you have a coin and you know that it will probably one half of tosses it will be let's call it 0, and one half it will be 1. But you have done an experiment and you obtained that here we obtained 5 511, and here we obtained, I don't know, 489, we have 1000 tosses. But if you want to compare, basically this cross entropy is a measure of how distinct from the ideal distribution this situation is, and you can think of this is of how unlikely you will get this kind of situation. What is the likelihood that you will obtain this? Well, actually, it's not the probability that you will obtain these results, but it's the likelihood of a true distribution of the situation when you have equal distribution of probabilities when obtained the results. So yeah, I don't know if I'm clear. And the cross entropy is a really interesting concept, and you should watch a particular lesson that's for this loss. Yeah, but you can think of it if just you take two distributions, one distribution and second distribution. Okay, so you take two distributions, and the cross entropy is a measure of how they are similar. Yeah, so as I said, you take every vector here, put it into cross entropy loss, and sum these values over each pixel. So this pixel compared to this pixel here, yeah, and these are two passed into the loss, and these losses are summed over the picture. But I think about what is bad for this loss. The bad thing is that you treat every pixel the same. You treat every pixel the same. So, in the case that you have two objects and one object is big and the second object is small, you probably want to determine whether there are two objects and be not so sure about the particular shape of the big object, but it's usually more important to know that there are two different objects, and the size of object is like an auxiliary information that is not so important. And in order to express this intuition about objects count and about the size of objects that you're segmenting, that you're classifying, there is another way of evaluating the model. It's called dice coefficient. So it's somehow it's measure of overlapping between two samples. When you have ground truth image like this, and here you have like this is the region where some object is, and our network predicts another picture. I'll just draw it on the top. Our network predicts another object. We take the union of this, not union, but no, how do you call? The region which is contained in both of these regions, in both predictions and ground truth labels, and you compute the size of this image of this region just by counting the pixel count in this region, and subtracted by the size of these whole regions. So what it denotes is, so if you have only small objects and they're overlapping they are overlapping a lot, it will be the same value if you have two big objects, and they're overlapping a lot too. But if we will use the previous loss, this value from here will be smaller than value from here. Yeah. So the region, the size of region of overlapping is does not affect our loss. We only care about the relative size. So this loss denotes that if we had a small object, on a picture, we have not predicted it at all, then the drop in the cost will be the same as if there was a big object in the picture and we were not predicting it at all too. And so this formula can be written in terms of element-wise multiplication. So here, for example, we have prediction, and here we have target. We just multiply it one by one, and this will be the intercepting region. So because here we have zeros, yeah, and here we have almost zeroed values, and then when we masked, so this is our this region, these values correspond to overlapped value, and we just sum this up to obtain this value. And the size of these regions are just sums of this is like the model of A, and this is model of B. They just sum over these matrices, over these predictions. Yeah, here we will just obtain the size, the count of pixels, and here we will obtain not particularly the count, but rather it's something like, so when we have on the target we have a smooth, on the target we have a crisp distribution. Here is not a kitten, and here is definitely a kitten. And our network is predicting a smooth line. Yeah, and basically if you just sum up, you probably, this region will should cancel this region out, and like what we want in the network is to make these regions so small as possible. So these values should be so small as possible, and if we had a bigger image here, should be only zeros. Okay, so let's move on to the next part of our lecture. We will discuss now state-of-the-art, well, actually it's not a state-of-the-art, it's the approach that the state-of-the-art is based on. And this approach called feature pyramid network. Actually this the idea is to not only, let's just move. So here on this implementation, our predictions, we output these prediction vectors of size n, number of classes. We output only here. But the authors of the image pyramid, feature pyramid network propose to run the same classifier, the same model that outputs the predictions, the same classifier, run the same classifier here, and maybe even here. And then all predictions from these classifiers. So basically, these are not, I will talk about them as classifiers, but basically it's the same classifier that with the same weights that is applied to several like resolution maps of this model. Yeah, so here you can see how the model looks like. It's a bit different from UNet because it doesn't concat the inner features from the convolutional network. It adds them just by element-wise addition. And there is another trick. Yes, here we have just basically basic, for example, ResNet, and you obtain on several layers. After the several layers of this network, you obtain features from filters that are of different sizes, and the pooling layer is decreasing the size of every image layer, every filter layer. Yeah, so here this is the output of first convolution, for example. This is output of subsequent pooling layer and a convolution, and this is output of subsequent pooling layer and a convolution. Okay, so we have obtained the several layers of images, and what we do next is to, so we have the last layer. We just use a one-by-one convolution. Yeah, let me describe what is one-by-one convolution. It's basically quite a simple thing. So imagine we have this grid, yeah, and we apply a convolutional network, which is 2 by 2. We apply convolutional network and obtain some vector, yeah, a convolutional filter. So these are outputs of different filters. Let's say there are p count of filters, and every output of every filter is multiplying by matrix of these and some nonlinearity. But the one-by-one convolution is basically a dense layer that is applied to this output vector. So it's like a dense connection to another sized vector. Let's say it's I don't know, q. So it's like applying a small dense layer just to a particular vector. You're applying a dense network here, a dense layer here, a dense layer here. To every pixel you apply a dense layer, and just if you had a stack of several filters, you can just resize the depth of the filter block. And they need to resize the depth of the filter block in order to run the same classifier, so-called head classifier, the same classifier on every feature map. So these blocks contain 128 depth. And these depths are different one from each other. They need to somehow align the depth of these filter maps. So yeah, we reshape the output filter map, reshape to a particular size. Then we upsample upsample this filter and add with another one, just element-wise adding, and then we use another one by one. We use another 3x3 convolution. It's just the particular implementation of from the authors, because here the upsampling is nearest neighbor upsampling. So we have these values from pixel, and if we upsample, if, for example, in this picture we have upsampled by 3 times, so we just use nearest neighbor when you just scale, and there is no interpolation, there is no transposed convolution, and because there are some anti-aliasing effects, they just upsample this and add the filters from the previous path, from the original network, and then they do the 3x3 convolution in order to it's something like similar to the result will be similar to transposed convolution, but I don't know, it's nice practice to test what will be better, to use nearest neighbor here on upsampling, or to use transposed convolution and do not use convolution after that. It's quite an interesting question. So yeah, and after that we have several feature maps of different sizes, and what we do is we try to for every patch of this feature map we run a special classifier that predicts a map of classes. So we have the whole feature map, yeah, and we divide this feature map into several regions, and for every region, which is of size in this work, it's 5 by 5. For every region, we run a model that outputs a map that is of size 14 by 14. That it is of size 14 by 14. But there is an obvious question you might encounter. So these are of different sizes, and how do you compare maps from here and from here? So when you will run this approach on different filter sizes, you will have different counts of this. So let's label this as 1, 2, 3, 4. You will have 4 like on this, 1, 2, 3, 4. This is, for example, here, and here you will have a much bigger elements, and you have 1, 2, 3, 4, 5, and so on, and there will be a much bigger size. So then they use just so-called bilinear interpolation of these maps. So they just basically upscale these 14 by 14 maps to correspond these. So then after the prediction, they stack them out. They stack them in this way, and just upscale these outputs and merge the results from here, from this classifier, from this and this, and you can see what is the size of corresponding patch on the image here. So to every 14 by 14 patch is upsampled to 256 by 256. It's kind of great when you think of it. So here is the classifier uses the high-level features. So when you're looking, for example, I don't know, when you're sitting on a beach, yeah, and you see a horizontal line is the line that will see everybody. So it's like when you have really bad sight when you wear glasses, you don't see details. You don't have crisp details. But what you will see definitely it is this horizontal line where there will be like sky and I don't know. Let our sea will be green and we will have sand, for example. And here on this level, our model just looks at these high-level features. It doesn't look in details. It just outputs some really vague picture that basically looks like a world of person that's wearing glass that has bad sight. And these models on the bottom, they used to refine our predictions. So if we have like something like this in our, so this is sand, yeah. We use this to refine our predictions to be more precise in the particular region of our segments. So, and what is great about it, so that these features are obtained conditionally of values of these features. So you first run here, you first have picture of general image landscape, I don't know, general image objects, and then you have these values, and they are telling one part from one side they are telling what is the global context, and then you just take here. You take local information. For example, these local filters, they can contain something like filters that are like gradient. Here will be 1, here will be 0. Yeah, so it will output a big value when here is ones and here are all zeros, and it will output a big value. So it will result to crisp edges. And these local features are combined with the global information, and then outputted. Then you obtain the local features that are conditionally on for example, we have sand here or we have sky here. So the results of even if we have the same patch here, for example, I don't know, we have a picture of a sand. If we have sand here, and if we put here a photo of a sand, yeah, so these and these will be different because of different predictions from this global scope. And let's move forward to the next model. It's called region-based methods. So what if we don't run the network on the whole image? The idea of region-based methods, they all called RCNN, or there are also fast RCNN, faster RCNN. So there are basically three flavors of these models. The idea is to use another classifier that will look at the image and produce a region of interest where to look. These models, as well as these ones too, because if you run another classifier here, you can use it in another task, for example, in object detection. And this model is used in object detection too. So when you're proposing these regions, you first look at an image and you see, here is like kind of similar similar pixels. So here will be probably there is no different objects, and here we have like blue and then we have brown. So this can be one object, this can be another object. This is a really simple algorithm that is can be expressed in terms of deep neural networks era, like computing just the similarities inside these pictures. These similar algorithms can produce lots of region proposals, but they are still less than if we try to use every single region crop. So they are just making a really bad guess, but it is good enough to reduce computational time. The approach is kind of similar with that we discussed here as naive approach. Let me find, yeah. So here, the problem was that we should run on every patch the whole convolutional network. But what if we use another network that predicts how we can what region we should choose to run the convolutional network on? So we will not be forced to run the convolutional network so much times. So yeah, basically the algorithm is simple. First, get rectangular regions using some simple algorithm, then wrap to fixed size. So here, if you have a rectangular that is not square, you need to wrap it because the convolutional networks operates on a fixed size image because it has a head that is dense. Network is determined how many coefficients you have in network. It is determined by it is defined by number of classes. And so then you resize this crop, apply some convolutional features, and classify regions. So this is how object detection works, and you can use an extension of this algorithm that's called mask RCNN. So this mask RCNN is a next generation of region-based models. When you first, the authors proposed to somehow mix different approaches. They first run the whole image is fed into convolutional network. Here is output of convolutional network. Then you use another network to predict the regions of interest. You crop them, you resize, you wrap them, and you put into another convolutional network. So it's like one network is converting raw image to useful features. Another network is selecting regions of useful features, and a third network is extracting, is transforming this region of interest to high-level features. And then you run a classifier that classifies the object that is in that region. Yeah, the mines. it's really hard to fit this for the first time. But like I'll repeat the same thing. We have the image, and we put this into convolutional, only one or maybe two layers of convolutional network, which computes different filters of this region. So it can be trained to perceive really useful features that are determining textures. It will determine textures, whether it's like solid or it's something like grainy. It gets these features. Based on these features, we use some algorithm that predicts region of interest, and then this region of interest is explored by a more complex, more deep convolutional network that that just runs and detects the object, classifies this object, and even more, we can take this output of this convolutional network and predict bounding box. We can make a regression task. So it's the whole module has starts to have loss that is composed of different losses. That is composed of loss from bounding box, composed of loss from classification error, and you can also run the same algorithm with upsampling to predict the map, the whole map from this particular patch of image. You can predict the segmentation map that we were discussing earlier. So this is a really advanced approach, and actually these were the state of the art until recent times. Actually, I think in about several weeks, Facebook research proposed a new model that was based on this architecture with slightly, well, there are more complications and more additions to it, but the basic idea is to use feature pyramid network. And also they solved a problem when they differentiate between different objects of the same class. So again, in the semantic segmentation, if we have semantic segmentation, we just label every pixel if it obtains to particular class or not. So, for example, for this image is if this pixel is a cell or if it's a background, if this pixel is a cell or if it's a background, and so on. But for so-called panoptic segmentation, the network has to determine different objects too. So it has to. It's if you have, for example, if you have, I don't know, several birds in the sky, the semantic segmentation will just label, here is a bird, another bird, another bird. These are all birds. But object detection and panoptic segmentation, they determine this is one bird, this is the second bird, and it's distinct from others. This is the third bird, and it's distinct from others. So you will differentiate between objects. And the state of the art, current state of the art, uses solves the task of panoptic segmentation. And so we'll actually finished. Here are a list of really useful articles and links. Here is a really great lecture from Stanford University that you should check out, and different articles that are just clarifying the articles that I was mentioning. So thank you for your watching, and hope you will enjoy your homework and seminar.